Dear students, welcome again. This is the last lecture of this slot relevant to the introduction of statistic, and I am again Ludovico Biagi from Politecnico di Milano. Today in this lecture we are going to deal with the least square interpolation, or in general the least square estimator. Why I decided to discuss specifically least squares? Simply because least squares are a very classical example of statistical estimators for unknown parameters, because they contain common principles that are also for other estimation principles, and because they are well suited for specific problems in managing geospatial data. The outline of the presentation is as follows. I will introduce the general problem. I will give an example of least square application by simply the fitting of a curve by observations. We will write the parametric model for the general case. We will write the stochastic model for the general case. I will provide you the final estimates of least squares. I have to anticipate that we will not deal with the proofs of the final estimates. I will just present the final estimates. And then we will discuss the covariance of the estimators. And finally, we will discuss the problem of the hypothesis testing applied to the least squares result. Okay, so let's introduce least squares for a very common and simple problem. The problem that is common to many applications is the determination of a function that fits in some way a set of m points that are given, a couple of points to be precise, TE and WE, where TE are given values. Let's think to a graph in which the abscissa is T and the ordinate is WE. TE are values in the abscissas, and WE are the corresponding values observed for the ordinate. The function we want to fit, we can call it phi, depends on a certain number of parameters that are less than the couples of given points. So let's call m the number of points, let's call n the number of the parameters of the function phi, and clearly the problem is to find the n parameters that characterize phi. In general, we can say, okay, that the abscissa values are known numbers or controlled variables, while the ordinate way are the values of a random variable capital way E, whose mean is the phi given at t. Note that to distinguish the observed random variables from the true values, we will use the symbol way O. Just for example, imagine that TE and WE are the values of two variables that are connected by a physical law, WE equal to a certain function of t. Often we can state that the values of TE are known exactly, while the values of WE have been observed with certain random errors. For example, TE could be the precisely determined epoch time, second, hour, day, whatever you want, while WE is in the imperfect measurement of a certain parameter, for example, the temperature of a chemical substance. We use the random character of errors to find an estimate of the fitting curve, taking into account the random nature of errors. So let's write the general model. We have a number m of random variables that we can call capital way E, whose mean is given by the following deterministic or functional mathematical relation. The expectation of the vector capital way is a certain vector way 1, way 2, up to way m, who is related to a certain set of unknowns that we will call x by the linear mathematical relation capital AX plus A equal to y, where capital A is a matrix with m rows and n columns. Normally it is named design matrix. The vector A is a vector of m values that are assigned, so constant and known. It is also called typically known term. So let's see what this means in the case of the fitting line. In the fitting line model, the model is simply that y is equal to b0 plus b1 that multiplies t. So the t of the population are given, the observed way of the population are given, the unknown parameters are the coefficients b0 and b1. So the functional model is y, vector y, equal to a vector of elements. Each one of them is given by b0 plus be t e. That in a matrix formula can be written as in the right of the first equation. A matrix whose first column is composed of 1, the second column contains the sampled t, and that multiplies a vector of two elements, that is the vector of the unknowns, b0 and b1. In this case, in this specific case, the vector A that contains the known terms is simply filled by zeros, as you see in the last equation of this slide. The pictorial representation is given in this slide. You have a Cartesian system. The abscissa axis contains t, the ordinate axis contains y. You have couples of observed values that are depicted as blue dots in this graph. For each couple of, for each point, for each blue point, this represents a given observation t and the observed value y. What we want to do is to find the straight line in this picture in orange that best interpolate all the points given in the observation vector. So in general, we can write the random variable capital Y E as the sum of two completely different terms. Capital Y is the expectation of capital Y plus a vector that we can name capital V, where the expectation of y is simply y. It is a vector of deterministic values that are the theoretical values of the observed capital Y, while capital V is a random variable that contains what we can call observation errors. We can also state that the capital V as a covariance matrix that we can write as CVV, that is given by a certain number sigma 0 squared that multiplies a certain matrix capital Q, where sigma 0 squared is also called a priori variance, and capital Q is an m by m matrix that is usually called cofactor matrix. Note that given the covariance matrix of capital V, we know also the covariance matrix of capital Y because it is clearly equal to the covariance matrix of V, and so sigma 0 squared that multiplies Q. As we have said, capital V can be interpreted as the observation errors, and we have to take into account that in most cases we can assume that the errors in the different observations of our population are described with a random variable that have the same mean equal to 0 and the same variance. Moreover, in the most of the application, the observation errors are not correlated, and so in these cases we have simply that the covariance matrix of capital V, that is the covariance matrix of the observations, is given by the a priori common variance that multiplies a identity matrix. So we have a problem in which we have observations that are observables plus unknown errors. We suppose to know the covariance matrix of the errors, and we want to find an optimal estimation of our unknown parameter. For example, let's go back to our example of the best fitting line. In this case, we have to estimate two parameters, b0 and b1, and in general we have to estimate n parameters, and the parameter can be obtained, estimated, by minimizing a specific target function that we can read in the specific case of the fitting line. We have to find the function phi, that is function of b0 and b1, given the vector of the observation. And in order to find it, we have to minimize the squared sum of the residuals that is written in this formula that clearly depends on the values of b0 and b1. More in general, the target function to be minimized is psi of weight up given weight 0 and given capital Q, the cofactor matrix, and can be written in a quadratic way, weight 0 minus weight up transpose that multiplies the inverse of Q, that multiplies weight 0 minus weight up. This can also be called as V transpose that multiplies the inverse of Q that multiplies V, where V are the residuals, differences between a posteriori estimated observations and available observation, and where the estimated observations must satisfy the equation weight up equal to capital A x cap plus A. So let's find the general solution to the general case where the cofactor matrix is not necessarily the identity. It can be proved that an optimal estimate for all the unknowns of the problem is given by the following formula. Let name normal matrix or capital N the product capital A transpose that multiplies the inverse of Q that multiplies A. We have for the unknown parameter x cap, the solution is the inverse of n that multiplies the transpose of capital A, that multiplies the inverse of Q, that multiplies weight 0 minus the known term. For the posteriori estimates of the observations, we have weight cap equal to capital A that multiplies x cap plus A. For the observation residuals, they are simply given by weight 0, the available observations, minus weight cap, the posteriori estimates of the observations. And we can find also an estimate of the posteriori variance that is given by the transpose of the residuals that multiplies the inverse of Q that multiplies the residuals divided by the number of observations minus the number of unknowns. So, for the specific example of the line fitting, where we have two parameters to be estimated, where we have supposed that all the observations have the same precision and are uncorrelated, we find out that the normal matrix reduces to capital A transpose that multiplies A, and the normal matrix, the inverse of the normal matrix, is given by this 2 by 2 matrix in the left side of the equation. The first element is m, the number of the observations. The second element in the first row is the sum of all the measurement epochs from 1 to m. The same for the first element of the second row, while the fourth element, the second element of the second row, it is the sum of the squares of the measurement epochs. A transpose that multiplies weight 0 reduces to a vector of two components. The first one is the sum from 1 to m of all the observations. The second element is again a sum from 1 to m of all the observations multiplied by their measurement epochs. Clearly, in a least square estimator that relies on observations that are random variables, all the obtained estimates are random variables, and so the estimates of the unknowns, the a posteriori estimates of the observations and of the residuals, and the a posteriori estimate of the variance are them two random variables. So, considering that all the estimates are random variables, we can also compute their covariance matrices. For example, for capital X, the estimate of the unknowns, we can apply the propagation law. We can make some very easy computation that is summarized in this slide, and at the end we find that the covariance matrix of capital X estimated is simply given by the variance that multiplies the inverse of the normal matrix. It is quite interesting to note that because the mean of the parameter estimations are completely equal to the vector of the theoretical parameters, we can say that this estimator is unbiased, and this holds for all the estimates. Again, by the covariance propagation, we can find out the covariance matrix of the a posteriori estimated observations, capital C way, and it is given by the variance that multiplies the design matrix, that multiplies the inverse of the normal matrix, that multiplies the transpose of the design matrix. Finally, for the a posteriori estimates of the residuals, we can obtain their covariance matrix again by covariance propagation, and in particular after few computation we find out that the covariance matrix of the a posteriori estimates of the residuals is given by the variance that multiplies the cofactor matrix minus the design matrix that multiplies the inverse of the normal matrix that multiplies the transpose of the design matrix. Now, an important point for what will be explained in the following. We are supposing that the errors have a normal distribution with a zero mean and a given covariance matrix. In this case, we will be able to determine the distribution of all the least square estimators. And as we will see, the knowledge of this distribution will allow us to state some conclusions about the quality of the solution we will have obtained, and in particular this knowledge will allow us to perform the so-called model testing and identification of outlier in individual observations. Okay, let's move to the distribution of the estimates. First point, it can be proved that when the observations are normally distributed and their errors have zero mean, the estimates of the unknown parameters are distributed accordingly to a normal distribution centered in the value of the unknown parameter with a covariance matrix that is given by the posteriori variance that multiplies the inverse of the normal matrix. Moreover, it can be proved that two quadratic forms follow a specific distribution. In particular, the quadratic given by capital X cap minus X transpose that multiplies the normal matrix that multiplies capital X minus X divided by the variance follows a chi-square distribution with n degrees of freedoms. And the quadratic form given by capital X minus X transpose that multiplies the normal matrix that multiplies capital X minus X divided by n that multiplies the a posteriori variance of the estimates is distributed accordingly to the ratio between a chi-square with n degrees of freedom divided by n and a chi-square with m minus n degrees of freedom divided by m minus n. That is the so-called Fisher distribution with n, m minus n degrees of freedom. In particular, the chi-square distribution is a density function that depends only on one parameter that is called degree of freedom. The chi-square distribution is the sum of a sequence of independent squared standard normalized random variables, as it is written in the formula above. In this table and picture, you find above the picture of a chi-square distribution, and in the following, in the table below, you find for different degrees of freedom the chi-square such that the area of the integral of the distribution at the left is smaller or equal than a given significant value. The Fisher density function depends on two parameters on the contrary. It is the distribution of a ratio between two independent chi-square random variables, each one of them divided by its own degree of freedom. So we have a chi-square with L degrees of freedom divided by L over a chi-square with M degrees of freedom divided by M. In this slide you find above a sample picture of the Fisher density function. In the table you have in columns the degrees of freedom of the denominator, and in the row the degrees of freedom of the numerator, and in the tables the Fisher values for which the integral of the distribution at the left is smaller or equal than 95%. Now an important point. It can be proved that when the observations are normally distributed with errors that have zero mean, then it can be proved that m minus n multiplied by a posteriori variance divided by the a priori variance is distributed accordingly to a chi-square with m minus n degrees of freedom. This is a very important starting point because it is the basis for any hypothesis testing on the results of any estimation by least squares. Okay, let's focus now on the problem of hypothesis testing. The starting point is that it can be proved that least squares are not robust. This means, in practice, that the final estimates of the unknowns and also the posteriori estimates of the observations and therefore of the residuals can be distorted when the functional model and the stochastic model are wrong. What does it mean in practice? Let's suppose that the design matrix is not properly written. This is an error in the functional model. Let's suppose that the cofactor matrix of the observations is not the right one. This is again a stochastic error in the model. This means that in our observations at the global level or at the individual level, outliers are present. So, how to identify outliers? By hypothesis testing. The definition of hypothesis testing is simply to determine if, with a fixed probability of error that is named confidence level, an hypothesis age 0 can be accepted. How hypothesis testing is performed in general? A statistics is built whose distribution is known when age 0 holds. While when age 0 is wrong, this statistic assumes values very high. So, the sample value of the statistic is compared to an acceptance interval. The hypothesis age 0 is accepted if the sample value belongs to this interval. It is rejected when the sample value exceeds the given acceptable interval. The test significance is the probability to make an error by refusing age 0, and the significance is usually put to 0.01, 0.05 or even 0.10 that respectively mean 1%, 5% or 10%. Now we are going to discuss two specific hypothesis testings that are the chi-square test or the global model test and the test on the individual observations that are specifically designed for least square results. The chi-square test is named also test on the global model because indeed it allows to check the global correctness of the starting model adopted for least squares, and the test on the individual observation is clearly, as the name says, just finalized to identify possible individual outliers in the observation. Let's start with the chi-square test. The fundamental hypothesis, I mean age 0, is that the posteriori variance is equal to the a priori variance. The statistic that has to be computed and submitted to the test is the ratio between the posteriori variance and the a priori variance multiplied by m minus n. This empirical statistic should follow under age 0 the chi-square distribution with m minus n degrees of freedom. So, the first step is to compute the empirical chi-square, and then we will compare it with the theoretical least square. The next step of the test is to decide the significance level of the test alpha, that, as I've said before, could be put to 1%, 5% or 10%. This is a user choice, basically. Once the significance level has been decided, given the degrees of freedom of the problem, by reading the chi-square table, we can find out the chi-square threshold such that the probability to have the empirical chi-square at the left is equal to 1 minus alpha. The probability to have the empirical chi-square at the right of the threshold is equal or smaller than alpha. In the picture you see, in the graph, you see the chi-square density distribution. You see a threshold value chi-square m minus n of alpha. At the left of the threshold value you have the area 1 minus alpha. At the right of the threshold value you have an area equal to alpha. Now you check the empirical value you have obtained by the ratio of the posteriori variance and the a priori variance multiplied by m minus n, let's say empirical chi-square. You have two possibilities. The empirical chi-square is smaller or equal than the threshold value you have decided. In this case, you can state that age 0 is accepted, the global model works, and probably no significant outliers are present in your dataset. In case the empirical chi-square exceeds the threshold value, you need to reject age 0, and so you have to hypothesize that probably there are outliers individual or also at the global level in your observation set. So, summarizing, the practical steps to perform the chi-square test are the following. First of all, we apply the least square principle to estimate the unknowns, the a posteriori estimates of the residuals, and the a posteriori variance. Now, given a certain significance level, you can determine the chi-square threshold by tables, and then you can compare the empirical chi-square with the threshold value. Note that the test on the global model originally has been designed and proposed to identify errors in the deterministic model, I mean the mathematical relation that was at the beginning written between the known parameters and the observations. But in principle, the global test can fail just because of errors in the stochastic model. For example, the a priori variance is wrong, or some element of the cofactor matrix is wrong. In case the chi-square test failed, in the worst case we have problems in the whole model, either deterministic or stochastic. In the best case we have just isolated outliers that are present in the observations. Against them we can apply some data smoothing or outlier reaction. That is exactly the step of the test on the individual observations. As a general note, I can say that sometimes one or two individual outliers in a very redundant problem do not cause the failing of the chi-square test. So my practical personal suggestion is that when you, even in case the chi-square test succeeded, it is better to perform also the so-called test on individual observations, just to be sure to isolate possible individual outliers. The test on individual observations is based on the fundamentally age zero hypothesis that the residuals of the observations divided by their standard deviation must follow a Thomson distribution with m minus n degrees of freedom. The symbol used for the Thomson distribution is the Greek letter tau. And here you see the formula, and remember that the denominator you have the standard deviation of the estimated residuals that is given by the diagonal element corresponding to that residual of the covariance matrix of the residuals that we have written well before. So the working steps for the local test on the individual observation is as follows. Oh yeah, I forgot to say that this test can be done, applied iteratively on each one observation from the first one to the last one. Here you see a picture of the Thomson distribution. It is a distribution with two tails, exactly as the normal distribution, and as zero mean. So again, it works exactly as the chi-square test. You have to find a threshold value tau such that the probability that your empirical value of tau is in modulus is comprised between 0 and the threshold value is equal to 1 minus the significance level. If the experimental value is comprised between these two limits, age 0 is accepted. If the modulus of the experimental Thomson value is bigger than the thresholds, you have to react age 0. Please note, it is quite obvious, but put specific attention to the fact that it is a two-tail test. This means that the age 0 hypothesis is reacted both if the normalized residual exceeds positively or negatively the threshold values. Now a second remark. Let's note that the not robustness of least squares complicates from a practical point of view the identification of individual outliers. Indeed, we can see empirically that when also just one outlier is present in our observations, its presence modifies also the residuals of all the other observations. So probably when you have just one or two outliers in your population, the Thomson test applied as the theory states could fail also for other observations. So it is better from a practical point of view to implement an iterative process that is empirical, and it is called data smoothing. So Empirical data smoothing is performed in an iterative way. The idea is as follows. At the first iteration, you compute all the residuals. You divide all the residuals by their standard deviations. So you obtain the so-called normalized residuals. Then you check them. You check where is the maximum normalized residual, and you check if the maximum normalized residual exceeds the Thomson threshold you have set up. When you have such a condition, you eliminate the biggest normalized residual without checking the others. You eliminate the residual, you eliminate from the original problem the corresponding observation, and you again estimate by least square the unknowns, and again the observations and the residuals. Then you submit to the hypothesis testing this reduced least square solution, and you again check observations for normalized residuals that are suspect. In case there is one, the biggest one of them, that is again too big, you eliminate this second observation, and so on. You iterate until the final convergence of the solution. With this slide, I finish my presentation on statistics. We started with probability. We defined the properties of probability. We defined random variables, their main properties, and then we put in parallel the theory of random variables with the errors present in observations. And finally, we discussed a specific case of statistical estimator that are the so-called least squares. Thanks for your attention by Ludovico Biagi of Politecnico di Milano.